class, Mr. Watlington. Welcome to week 2. I think week 1 went pretty well for everyone as I'm looking at your grades and everything. Now, going into week 2, we're going to be talking about some data representation and processors. Now, I will say, going through the material, the book, the textbook, it really gives us some very good information, very good instructions. But one thing I did kind of notice and is that it made the assumption that everybody had a quiescent level of knowledge already. So what I'm going to do today in this week's lecture is go over some of the basics again. And what I mean by that, because as I look at the class demographics, I see some of you guys have quite a bit of expertise in IT networking, and some this is just kind of moving into this arena. So we're just going to cover some of the basics. This will maybe be a review for some, probably for most, and probably not a lot of new material. So first, let's take a look at week 2 overview. What are we covering for week 2? Well, week 2 we're doing chapter 3, chapter 4. Chapter 3 is data representation. We talk about numbering systems, and there's some review questions in chapter 3. Chapter 4 is where we really start talking about the architecture of processors, okay, of your CPUs and microprocessors. And then there is the research problem. What you're going to be doing for your research problem for this week is looking at RISC. What is RISC? Your reduced instructions set computers. Really, there's two major types of computing architectures when we're talking about at the CPU level and how it deals with the code instruction is the complex instruction set and reduced set. And what you're going to do is you're going to compare Intel and the Italium processors and looking at the contrast and compare those. And of course, there is the week 2 quiz to be aware of. Okay, so let's do a little bit of review. Let's talk about numbering systems. Numbering systems. Again, hope this is a review for most of you, but I know sometimes we get kind of stuck if you're not dealing with this stuff on a day-to-day basis of understanding numbering. And you know, I like going back and look at the history of some things. When we think numbering systems, it's really 2 types, all right? You got non-positional numbering systems and positional. You're thinking, what are you talking about? Well, in the early days, years ago, when we counted, we counted really as almost object oriented. We counted on our fingers. We counted using rocks, stones, pebbles, sticks, whatever it was. And those objects, like I say, they described our numbering, how we would count. We use different types of symbols. And if you remember the Roman numerals, okay, it's based on symbols, okay? Different types of symbols. That is called non-positional. Now, what we use today in counting is called positional numbering. And what a positional numbering system is, like I say, there's a few symbols, we call them digits. And they have a much greater representation, okay? Depending on the value and the position of those digits. Okay, and what are we talking about? A positional numbering system is what we are really accustomed to, especially the decimal system, because that's what basically almost across the globe everyone pretty much uses this decimal system. It's called decimal because it has a base of 10. It means it has 10 symbols, 0 through 9. If you think about it, if you count that up, that's 10 symbols it uses. Is it used by humans? Yes. Do we use it in computers? No, computers don't understand decimal. Another numbering system that we use is binary. Has a base of 2, meaning that there's only 2 digits or 2 symbols in this numbering system, a 0 and a 1. Do we use this as humans? Not so much, other than teaching. Does computers use them? Yes. Pretty much everything your computer does is based on a binary numbering system, a 1 and a 0. You can think about that kind of as a switch, when we think things are binary, either on, off, dark, light, switch, on, off. So everything that's done within this computing system we're talking about is using binary. Another one is hexadecimal. Hexa, 16, hexa, 610. So there's a base of 16, and it has 16 symbols or digits from 0 all through 9. And then, since we can't go any higher than 9 with our original numbering, we use alphabets, A through F, to represent the other digits. So that gives us the base of 16. Is it used by humans? Here again, not so much, mainly for teaching purposes. Is it used by computers? Actually, no. You think, well, why are we learning hexadecimal? Hexadecimal gives us a great way to represent binary numbers, especially when binary numbers start to become very large. The hexadecimal just is a great way that now we can represent a large binary number in a much smaller space. Let's walk through these. So when we think about decimal numbering, right? What's the base? Base 10. How many digits? 10 digits, starting at 0. Yes, 0 is just as important of a digit in a numbering system as 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to count 0. It's not just a placeholder, as it was told to us many years ago. It's just a placeholder. No, it is an actual digit. It's the symbol. So we got 10 digits, 0 through 9. And now, let's look at an example. You're probably thinking, is he actually teaching me 6th grade numbering? Yes, I am. Because, so amazingly, many people even don't understand our own decimal numbering system. It's really talking about places. Let's take this number right here, 7,475, right? What does that really mean? What does that really mean? Well, if you look at the places, the placeholders for each of these positions, over here, this is 10 to the 0. Now, thing to remember, any number raised by 0 is always 1. So 10 to the 0 is 1. Any number raised to the power of 1 is that number itself. So 10 to the 1 is 10. 10 to the 2, which is 10 times 10 is 100. 10 to the 3 is 10 times 10, 100 times times 10 is 1,000. So that is the value of each of these boxes. That's the 1, that's the 10s, that's the 100s, that's the 1,000. Right? So we're looking at this example that says we have 7,000, or 7 times 10 to the 3. We have 400s, 4 times 10 to the 2. We have 70, or 7 tens, 7 times 10 to the 10 to the 1. And we have 5, which is 5 times 10 to the 0. 5 times 1 is 5. That is those placeholders. And its decimal equivalent is just what it is, 7,475. That is our decimal numbering system, right? Yeah, a little bit of review there. All right, now how do we equate this to binary? Okay, let's look at the binary system. In binary, the base is 2, which means we have 2 digits, a 0 and a 1. That's as high as we can count to. 0, 1, 0 or 1, 0 or 1. Very binary, yeah. Okay, now let's take a look at an example of that. We're going to take this example, 1, 1, 1, 0, base 2. Now, the places are the same, okay? It's just the base is different. So now, if I look at this first position, which is 2 to the 0. And like I said, any number raised to the power of 0 is always 1. Any number raised to the power of 1 is always that number. So 2 to the 1, this is the 2 to the 1 position, which is 2. 2 to the 2, which is 2 times 2 is 4. And 2 to the 3, which is 2 times 2 is 4, times 2 is what? 8. So this is the 8 position, that's the 4 position, the 2 position, and the 1 position. So if I put in a digit into each of those positions, I have 1, 1, 1, 0. Okay? So what does that actually equate to in a decimal? The decimal equivalent of that would be 14. And you may say, well, how did you get 14? Let me show you. So if I take each one of those positions, which is 0 times 1, that's basically what I'm doing here. 0 times that 1 is, yes, 0. 1 times 2, 1 times that 2. Just doing the same type of math we did in the decimal. Is 2. 1 times 4 is 4. And 1 times 8 is 8. And if I add those together, 2, 4, 8, and 0, it equals 14. No different than if I do in the English, in the decimal, if I add 7,000 plus 400 plus 70 plus 5 gives me 7,475. So you see the process, the procedure doesn't change. The only thing that changes is the radix, or the base of that numbering system. Let's take a look at one more, hexadecimal. This is the one that really throws people a lot of times. Why? Because we got to start using alphabets. Because there's 16 bits, or 16 digits, and that's from 0 all the way through F. Now, where does the F come from? Well, I can only count, right? There's only 9 known digits. From 0 to 9, 10 known digits from 0 to 9. That's how many known digits we haven't made up any new. So now to represent 10, which 10 is what? A 1 and a 0. I have to use the letter A. 11, which is 10 plus 1, is the B. 12 is a C, 13 is a D, 14 is a E, and a 15 is F. So basically these alphabets are representing these numbers. That's all you have to remember. It's not anything difficult. Okay, let's take a look at the math. Let's do an example. So now if I say 2F 4D, okay, 2F 4D, and I plug those in. First, let's do the same thing, and we got to compute what each of the positions are, because the base is 16 now. So 16 to the 0, like we say, is what? It's going to be 1. Any number raised to the power of 0 is 1. 16 to the 1 is itself, 16. Any number raised to the power of 1 is going to be that number. 16 to the 2, that's 16 times 16 is 256. 16 to the 3 is 16 times 16, which is 256, times 16 is 4,096. Now you see how quickly these numbers got huge? That's why we like using hexadecimal. I can relate now a very big number with a very small amount of positions or digits, locations. Okay, so now if I put my example in here, 2F4D. D is what? D, if we come up here, D is 13, right? Actually, I got this worked out for you. So you see the decimal equivalent is 12,109. So like I say, so now we'll walk through this a little bit slower. So if D is equal to 13, where we get it from? Right up here. D is 13. So 13 times 1, that's here again, which is D. D is 13. 13 times 1 gives us what? 13. If we look at the next position is 4. That'll be 4 times 16. I don't have to do any fancy conversions here because 4 is 4. 4 times 16 gives us 64. F. What is F? F is 15. So 15 times 16 to the 2, which is 256. So now you have 15 times 256 is 3,840. And the last digit over here is 2. When 2 times 4,096 is 8192. And when we add those together, 13, 64, 3840, and 8192, that's what gives us 12,109. So those are the 3 basic numbering systems that we work with. We work with the decimal system day to day. That's what we use on this planet to count with. Computers use binary, all right? I mean, everything that was running, we talk about those ones and zeros. That's where they come from. And hexadecimal is a way of representing very large numbers within a very small set. Because I can take 4 positions and I'm already up to 12,000. So that's why we like hexadecimal. Numbering systems. Now, when we think about numbering systems, why that's important? Because everything that we're doing inside the CPU is based on some type of instructional logic. And think of logic in the same way. Yes, no, it is a binary type of activity. That's why logic works great that's why binary works great in our processors, because it can support logic. And what is logic? Especially when we talk about the gates themselves. Like I said, these are your basic building blocks of any digital system. Like I said, so really they're electronic circuits where you can have one or more of these inputs put together, you can string them together, and the output is based on some type of logic. Now, here again, the text does a great job, the PowerPoints and of explaining this into detail, but I kind of wanted to back it up a little bit and just to be sure everybody understood from a basic construct. Different types of gates, and really the one we like to start with is an AND gate. AND meaning that, just that. I have to have, both inputs to get an output. So if I walk through, 2 strings of data going into this AND gate. So there's a 1 on that input and a 1 on that put. AND says there's 2 inputs there and the output is going to be a 1. If I have a 1 on this input and a 0, well, they're not the same, so that output's going to be 0. Same thing, a 0 and a 1 is going to give me a 0. A 0 and a 0 going to give me a 0. The only way I get an output on an AND gate is that both inputs have to be 1s. Now, the next to that is also the NAN or not AN. And basically what you see, when you see, whenever you see a symbol and it has that little circle at the front, that means it's doing an inversion, right? So it's inverting that. So now a 1 and a 1 is going to give me a 0. A 1 and a 0 is going to give me a 1. Same thing, a 0 and a 1 is going to give me a 1. And a 0 and a 0 is going to give me a 1. So it just basically inverted the output. And meaning things have to, both inputs have to be the same to get an output. Other type of logic that we use quite a bit is the OR gate. That's kind of the either or. So it means that if I've got a 1 on any of my inputs, if there's a 1, I'm going to get a 1 out. A 1 and a 1, yes, there's a 1, I'm going to get a 1 out. A 1 and a 0, going to get a 1 out. A 0 and a 1, going to get a 1 out. The only time I don't get a 1 out is when there is no 1s at all on either of the inputs. And the NOR function, here again, as you see, it inverts that. It inverts that. So that's the OR function. Now there's one other we're going to talk about, because this is a very peculiar type of gate that we call the exclusive OR. Exclusive OR. You see this used quite often in computing, in programming, as well as in encryption. This exclusive OR gate is really probably the heart and soul of what undergirds the mathematics and the logic that we use in encryption and cryptography. And what an exclusive OR means that for it to get a 1 out, it has to be exclusively an OR. Meaning here, that's not exclusive. I have a 1 on either gate. Not exclusive, so I'm going to get a 0. Now I have a 1 on exclusively this gate. I get a 1 out. I have a 1 on exclusively that gate. I have a 1 out. And I have no 1 at all, so I get 0 out. So, but yeah, this is one that you will see in a lot of different applications. So those are really your basic types of gates. Now, another way that I like to look at gates and look at logic is from a biblical perspective. You can say, what? Yes, from a biblical perspective. Let's think about the OR, the logic of OR. And I like using this right here. The Father, the Son, and the Holy Spirit. The Father, or the Son, or the Holy Spirit. They all make up and represent the Godhead. And so when we talk about that Godhead, whether you're talking about Jesus, whether we're talking about God himself, whether we're talking about the Holy Spirit, they're 3 in 1. So, either one is a direct representative of the Godhead. Now you may say, okay, what about and? How do you get an and function logic out of the Bible? To me, this is probably one of the most fundamental. How to receive salvation. To receive salvation, this is not an OR function. If you go to Romans 10, 9, and 10, it says what? Confess with your mouth and believe in your heart. Okay? And believe that Jesus is Lord. Meaning that you have to confess. You have to believe. But not only believe what? Believe that Jesus is Lord. So those 3 things, that's an and function. Because it's not an or. You can't do this and this. Or you can't do this or this. You have to do this and this and this to get you to receive salvation. So yeah, so you see every day our Christian walk is really based on OR logics. It's based on and logics. And there are some things that are also exclusive. Anyway, that's your Bible study for today. All right, let's switch gears and talk about CPUs. Week 1, we covered some CPU fundamentals, right? Since we talked about the decode, the execute, the store, the fetch cycles. Well, this week we go deeper into that in the lesson. Also talked about kind of what they look like, where they sit on the motherboard, the different types of memory, whether it's registers, cache, and or different types of RAM memory. But this week, actually, I want to take it a little bit different direction. What happens? How does the CPU work? And this is going to be a pretty corny analogy, guys. I know. But hopefully it helps you if you're not really familiar with it. Let's look at what I call the man in the box analogy. Here's a CPU, right? And that inside that CPU, we have this little guy in the box. Yes, he is ready to do some work. That's your CPU. He is ready to become active and do something. However, one, the problem, there's a couple of situations. He will gladly do what he will perform any task that you want him to do. But he can't see or hear anything outside of that box. So we got a problem. How do we communicate with the guy in the box? Okay? Well, the way we do that is what we call external data bus. Actually, your CPU communicates with the outside world across your external data bus. And these are a series of wires that connect to that CPU. And now you see, start seeing a couple things we start tying together here. This is where your binary come in. So these are light bulbs. Let's imagine these to be light bulbs. And every time a bulb turns on here, it turns on inside the box. And that's how we're able to communicate with the man in the box so you can see the bulbs. So if I have an 8-bit computer word, meaning that there are 8 pieces of wire running across this bus, and each one can carry a 1 or 0. So now I have programmed this external data bus with 10110001. I've turned on those lights. So inside the box, I have the same thing. So the little man in the box, he can see these lights coming on, which tells him something. We don't know what it tells him yet. So that's how now I'm able to communicate with the CPU, is across that data bus. However, we have a problem. This little man in the box, he doesn't have any memory. So he needs help saving whatever information he's working on. So he has no memory. So how do we help him out with that? Well, it's the thing we call registers. This is what registers are. Inside the box, you have registers. And depending on the system, you basically have four types of registers: the AX, BX, CX, and a DX register inside of that box. And this is just memory. It's very fast memory, but very small amounts that registers. So now we can transfer things coming off of this bus into a register. So let's say this code, this 8-bit word came trucking in. Boom, turned the lights on. The lights on the inside of the box turned on, and now we can do something with it, right? We could, but here's the problem. There's always a problem, isn't it? Always a problem. The problem is the man in the box don't have any instructions. He's got workbenches. Think about these as workbenches. He's got, the lights turned on. I see that, but I don't know what to do with it. He's in the box, with no instructions. So what do? Well, that's where we have what we call a code book. That's the tool that this little man in the box is going to need, or the instruction set to tell him this is what you need to do with these, with the ones and zeros, with the words that are coming in across the bus, and it tells him now this is what you need to do with those. Like I say, now this code book, it's written in what we call machine language. Machine language is written at the ones and zeros level. It's written to where the CPU can understand it. Now, most of the languages that we work with day to day is not machine language, like C++, C++, all those. Those are high order languages that's made to talk to humans, so that we can read it. But somewhere along the way, if we're writing a program in C, C++, whatever it may be, it has to be translated to machine language before that CPU can execute and understand it. Okay, it has to be transcoded into machine language. Got to be good, because that's all that CPU understands is machine language, no matter how sophisticated our higher level languages get. So one command is what we call a line of code, and then the complete set of commands that a processor needs, that's called the instruction set. Give you an example of what that looks like. So let's just talk about those lights. So let's say if I turn on the first light and the other 7 are zeros. The instructions is really what it's saying. It says the next line is a number and put it in the AX register. So now the little man in the box got some instructions. Okay, he knows that when these lights come on, I need to take that and put it in the AX register. And now the next 8-bit word comes in and it gives me these lights on. The number 8 light and the number 5 light. And everything is the zeros. That tells him that, because he can look at his instruction book and decode that, says the next line coming in is a number. Put that in the BX register. So you take the first one, AX register, next one, the BX register. Then the next line comes in, turns on these lights, and that tells him to do what? Add AX plus BX and put the results, in a register. He could put that in CX if he wanted to, or he could just leave the results in AX. So, but either way, he's got instructions. And then these tell them what the numbers are. This tells them what the actual numbers are going to be. So anyway, so now you've got instructions. So we should be good to go, right? Almost ready to work. Like I say, because now we've got the little man, we've got data coming in on the data bus, we've got his workbenches, which is these registers, he's got the instructions, which is his code book written in machine language. Only one problem. He doesn't know when to start. There's always a problem, isn't it? So how do we rectify this problem? That's why we need a clock. That's why you have a clock, because that clock is that tells them when to start and when to stop. If he didn't know that, all he's going to get is a bunch of jumbled stuff coming in together. So the clock tells them when to start, when to stop. And this is your clock cycle. When we talk about a clock cycle, that's a up and a down. That is one clock cycle. From here, up, down, here. Another clock cycle. Here, up, down, here. So if we see here represented as 2 full clock cycles. So now we got a clock cycle coming in, and that clock is telling them, start now, stop. Start now, stop. Start now, stop. And every time he starts now, he's going to take an 8-bit word, bring it in, read the instruction book, put it in a register, do something with it, and the next clock cycle, he may push that back out that direction. Once he's, let's say, bring a number in, put it in AX. Bring a number in, put it in BX. Now, next clock cycle, add AX and BX. Next clock cycle, push that back out here. So you see, it takes multiple clock cycles to do a complete instruction set. So I know in the text it does. It breaks down clocks and times quite well, because this clock could be working in the megahertz range, which is a million cycles per second. It could be working at the gigahertz range, which is a billion clock cycles per second. So it could be working very fast. And that's the magic of what we think of our computing now. Is it's very sophisticated. No, it's doing very simple things, but it's doing it really fast. So it appears that it's doing a lot of really complex things. So this is how your CPU is working. Based on the clock, you're getting a computer word in. Like I said, this is just an 8-bit word. Now, if you look at most of our computers today, they're what? 64-bit. You still have 32-bit. But 64-bit words, that's what? That's 8 computer words at one time. 64 bits that's being pushed into that CPU. 64 bits is being processed. So that is why the instruction set has to be the same. So if you're running Windows, let's say Windows 10, and using Microsoft Word, you have to be in that 64-bit program mode for it to know that. Now, there are some operating systems can still operate at 32-bit, yeah, and it's okay, but it all has to be synchronized. Because 32 bits means that we got 4 8-bit computer words being pushed in here at the same time. For this example, to keep it simple, we just use one 8-bit word. 8-bit word comes off the bus, goes inside the box. The man in the box looks at the instruction set and knows to bring it into a register, bring things into registers, do some type of processing with those, whether it's addition, subtraction, multiplication, or division, or doing a comparison. It may be doing a comparison and using different types of gates, AND gates, OR gates, NAND gates, NOR gates, to do those types of mathematical computations. Not very complicated, but it is able to do this really quick. And some computers where you may have multiple processors or multiple cores, so it is able to do multiple things at the same time based on that clock rate. Okay? Hopefully that helped you out to understand what's going on with the CPU before you kind of jump off the deep end of the diving board and get into some of the terminology and a lot of the great stuff that the book and the PowerPoints are teaching you. So like I say, you know, when you think about clocks, simple instructions, something that's very simple, could require a single clock cycle. If you're talking things that are complicated instruction sets, it may take multiple clock cycles to get that one thread, that one process done. And that kind of leads you, hopefully now you start thinking, now I see the difference between RISC, you know, the reduced instruction set and the complex instruction set computing, because it has to do with clock cycles and how efficiently, and there are trade-offs. There's good and bad with both. All right, guys, what did we talk about in this lecture session? We went over numbering systems. We talked about the analogy of, you know, the little man in the box of the CPU, and you know, then from there we covered your external data bus, registries or the memory, the execution, how code is executed, what we call the execution code book, and clock cycles. Hope this helps you out to understand and to see the bigger picture of what's going on. Now dive into the deep end of the pool, and just, you know, just make it happen. Make it happen. Hey, look, great time we're having, because I think it's a great class. You're gonna walk away from this knowing a lot about the inner workings of a computer, of an operating system, of the CPU, of memory, and all these different components. So take full advantage of it. All right, God bless you. Have questions, you know, please contact me, and looking forward to a great week 2.